Okay, good morning, everyone. The morning session is about hadron physics. It's a pleasure to me introduce Professor Adnan Bashir. Professor Adnan is professor en la Universidad Michoacana en Morelia, México. The talk is about internal structure of hadrons, understanding strong interaction, and the standard model. Professor Adnan, you have 1 hour, including question or comments, okay?
Button here on my screen, so I don't think I'll be able to change anything or see myself or see anyone else. First of all, let me start by thanking all the organizers, including Eduardo Rojas, who I have had the pleasure and chance to work with. I'm very sorry I cannot be with you today in person. It's in fact my personal loss. Colombia has been a great pleasure to visit, and I wish I could be there in person. Now, I would also now like to say that I looked at the program of the conference, and it's of course a large conference, Colombian High Energy Physics meeting, which covers a lot of topics. So hadron physics and QCD is only just one part of it. So I understand that in the audience, there are people who are specialized in various different fields, and also there are students. So I will try to keep it a bit more general. There are parts of the talks which are a bit more specialized, and a part of them are a bit more general. So I will focus more time, give more time to the part which is more general, and spend a little less time on the details which might not be as interesting and useful for many of you. Okay, so after all this preamble, I'll start talking about the internal structure of hadrons, understanding strong interactions and the standard model. Okay, the title, in fact, does not talk about quantum chromodynamics, but as we all know, that behind the internal structure of hadrons and behind the strong interactions and a part of the standard model is what we call quantum chromodynamics. And as you may know, that last year people were celebrating 50 years of the initiation of quantum chromodynamics. Okay? So the work of Pulitzer and Gross and Wilczek led us to the understanding of perturbative QCD or asymptotic QCD. When the quarks we understand are very, very close to each other, then they do not really experience the force among us. The force becomes weaker as they come closer to each other. And this fact was described in 1973 by this elegant theory of quantum chromodynamics given by these gentlemen who achieved a Nobel Prize in 2004. But hadrons, the strong interactions, have lived even before the advent of understanding this fundamental force between them. So we have to go back a little bit if we want to know what they were. So about 9 years before the advent of quantum chromodynamics, Gell-Mann had already given his what he called eightfold way to suggest that all hadrons, which of course include the neutrons and protons, forming the core of different elements that we know exist, are composed of quarks. And of course, quarks are unusual properties. They have strange electromagnetic charge, fractional electromagnetic charge, and they have, as we now know, color. But at that point, there was strangeness and other flavor properties that were associated with these quarks by Gell-Mann. So they had isospin and strangeness. Now, if we go back even further in time, what we know is that I think in about 1932, there was an interesting time when Heisenberg had told that, in fact, proton and neutron were two different facets of the same nucleon. And later on, Yukawa was of the idea that neutrons and protons, they are, an isospin doublet. And just like a spin up electron and spin down electron exchange electromagnetic force with each other through the exchange of photon, that this up nucleon and down nucleon in the isospin space exchange forces by the exchange of mesons. So he gave this idea in 1934, and just 2 years after the discovery of the pion, he was given a Nobel Prize in its own right. So all these people whose faces have been shown here got the Nobel Prize on this subject. In fact, Cecil Powell, who had discovered the pion due to the start of new experimental techniques in 1947, he himself got a Nobel Prize in 1950. And more interestingly, Nambu in 1960 wrote a couple of very interesting papers trying to understand how come that proton and neutron are quite heavy and carry most of the mass which is there in the hydrogen atom. So by that time, Gell-Mann had not given the idea of his quarks, but Nambu does mention of the existence of some primary fermionic field inside a nucleon, which breaks chiral symmetry in some way, which might be the reason why proton and neutron acquire a large mass. Now we can go even further back, and I would consider that probably the discovery of nucleus by Rutherford was the discovery of the first strongly interacting particle. That was the gold nucleus. So we can call QCD a golden theory in that way. So Rutherford did scattering experiments with various nuclei, and of course discovered that the hydrogen nucleus was the lightest in, I think, around 1917 or 1918. It was called the proton. So the history of strongly interacting particles is almost as old as the University of Nariño, which is celebrating its 120 years of foundations. So it's more or less the same time. Okay, so now that we have talked about this QCD and also talked about the strongly interacting particles, I think one of the things that of course attracts attention is to talk about how the bound states are formed in these interactions, and how these bound states in fact tell us about the underlying theory which in fact produces this structure. So we can date back to, of course, knowing the hydrogen atom. When Rutherford had discovered the nucleus, he immediately sent his results to another student of J.J. Thomson, who was Niels Bohr, and who was a theoretical physicist, and asked him to try to understand and interpret the results that he had obtained, which did not agree with the idea of J.J. Thomson of the atom. So then Niels Bohr came up with this Bohr atom that you can see right now on the screen. Okay? So that is probably the simplest bound state in quantum electrodynamics, which is a hydrogen atom. There is a proton and there is an electron around it, and that of course is what we study in our courses of modern physics, then Schrödinger equation, and after all that, then we also try to include through perturbation theory the fine structure and the hyperfine structure, which talks about not only the masses of these states, but their excitations and the transition between different energy levels, and that in fact gives us a deeper understanding of how electrodynamics works. If we go then further down the road in 1947, it was Lamb who discovered this experimental effect of what is now called the Lamb shift. It told us that 2s half and 2p half levels, although the fact that they have the same total angular momentum, they do not have the same energy levels. And in fact, one can study the transitions from a higher level, say P3 half, to these levels, and we can see that there is a discrepancy of about 4 microelectron volt, which is about 6 orders of magnitude smaller than the energy levels that we know exist in the hydrogen atom. That's a very small effect. And at that time, the only thing that people could understand and do in quantum electrodynamics was the tree-level calculations, and therefore this effect could not be explained. So there are many clever minds who started trying to explain this, and eventually it led us to the much deeper understanding of quantum electrodynamics. In fact, if we hadn't achieved that, then according to Dyson, what he said when he looked at the Lamb result was saying that if we do not understand the hydrogen atom, then we really do not understand quantum electrodynamics. And therefore, the understanding led us to what is called the idea of renormalization, and renormalized quantum electrodynamics then enabled us to understand Lamb shift. And not only that, we could go on to do other calculations in at much higher orders, like the muon anomalous magnetic moment, electron anomalous magnetic moment, and of course the Lamb shift itself. So understanding these bound states, these simple bound states, is really crucial for us to be able to see that we understand the underlying theory. In strong interactions, the simplest bound states you can say are the pion and the kaon. They're the two-party bound states in QCD. They're made of up quark, down quark for the case of pion, and for the kaon, we also have the strange quark. So if we have to understand the underlying theory of QCD, we have to understand the internal structure and how it goes about, both experimentally as well as theoretically. In some way, more exciting states that we know exist in reality are the protons and the neutrons, which form the nucleus of an atom. Okay, so these are considered to be the three-body simplest bound state in QCD. So these are what we want to understand to be able to have a better idea of QCD. And this understanding is even more difficult in a way than was in quantum electrodynamics, because it has emergent phenomena of confinement and hadron mass generation in quantum chromodynamics, which is in fact not a feature of other forces which form standard model of particle physics. Now, how do we understand the internal structure of these particles? Okay. After the scattering experiments of Rutherford, much later, then Hofstadter carried out some experiments in 1950s, early 1960s, in which he also studied the scattering problem. But instead of bombarding a gold nucleus with a helium nucleus, the experiments consisted of electrons being scattered from nuclei. So if there were point particles, different nuclei, then we would get the famous Rutherford result. But a deviation from this result could possibly tell us that they are not point particles, and in fact will give us an idea of the charge distribution between these particles. And those were the ideas behind Hofstadter's elastic scattering experiments of electron from nuclei. He did experiments on lots of nuclei, carbon, hydrogen, oxygen, and going on to lighter particles as well, helium and hydrogen, and tried to have an understanding of what were the dimensions of those nuclei and what was more or less the charge density which was there. So these experiments led us to this kind of understanding in terms of charge distribution and what are called in the momentum space the form factors of nuclei and proton and neutron. Then later on, the discovery of quarks and gluons in 1960s was based upon the experiments of deep and elastic scattering. Deep and elastic scattering gave us another concept of what are called the parton distribution functions. Feynman came up with this idea in 1969, again with a lovely article that he wrote, which almost has no equation in it. It introduces the idea of parton distribution function, in which they tell us how much each parton or quark or a gluon carries the longitudinal momentum fraction of the whole proton in this deep elastic scattering, because it's really the photons are able to isolate the quarks in deep and elastic scattering and interact with it directly at time scales which are very, very short. Okay. Then much later, in the works of 1990s and early 2000s of various leading researchers, the concept of generalized parton distribution came. It was in the experiments of doubly Compton scattering experiments. So in which the dependence of, in which we could give a three-dimensional structure of the nucleon, which not only looks at the Q-squared dependence of the energy which is given by the photon in elastic scattering experiments, but which is also a function of X, which is the longitudinal momentum fraction, and another momentum fraction which tells us how much is the off-forward element of these scattering and give us an idea of the transversity of these particles. So we can get a three-dimensional picture of this. Now it's good and interesting because there are many hadron physics laboratories which now try to study these GPDs, what are called the generalized parton distribution, and tell us the three-dimensional internal structure of hadrons. There are experiments being carried out, and there are experiments which are being planned for future. The idea is that if we understand, I mean, it's an important task, of course, to understand the internal structure of hadrons, but then there is a deeper level of understanding. How about the forces which, in fact, give this hadronic structure to protons, neutrons, pion, kaons, and all other particles? That is to say that once we understand or are able to draw this three-dimensional picture of hadrons, we should be able to see how they lead us to the footprints of the underlying theory of QCD. It is just like saying that if you had, the atomic structure, the spectral lines, then how can that lead us to quantum electrodynamics, which gave this structure to the atom? Right? So we understand the hadron structure and how it will lead us to the footprints of QCD. Experiment, I mean, of course, there are different approaches. People carry out the global analysis of experimental data. Then you have, of course, lattice studies, and you will probably hear one of the talks in this session. There are effective field theories, chiral perturbation theory, and there are Schwinger-Dyson equations based upon the continuum theoretical field description of quantum field theories in general and QCD in particular. So, in fact, this is the Lagrangian, which we all know of QCD, which is based upon the SU3 local transformations. Looks very much like quantum electrodynamics, but it has self-interactions between gluons of triple gluon type and the 4-gluon type, and the coupling involved in these interactions is not always small at the energy levels which are explored in experiment. And of course, we know that QCD, unlike other theories which form the standard model, has this emergent phenomena of confinement and mass generation for proton, neutron, and other similar hadrons. We all have known about confinement since late 1960s, but it's still an issue which we do not we are not able to resolve yet. We know that hadrons only exist as color singlet bound states. We can create in high energy experiments all kinds of partons, but of course, much before they reach the detector stage, they conspire among each other and they make hadrons, they make protons, neutrons, pions, they make all kinds of color singlet states and do not reach in the detector in form of any colored particle. And this is an interesting feature, an emergent phenomenon which we cannot see looking at the Lagrangian of quantum chromodynamics. And then we, of course, also know that our atoms and elements are mostly made of light quarks, which are up and down quarks, which form protons and neutrons. We also know that Higgs is a particle which gives masses to the fundamental particles through spontaneous symmetry breaking in the Lagrangian of the Standard Model. But these current masses, which owe themselves to the Higgs mechanism, are only about a few MeVs in case of up and down quarks. These quarks are put together to give a proton, whereas proton has a mass of about 1,000 MeVs, which is 2 orders of magnitude greater than the sum of these three current quark masses, which of course leads us to conclude that it is in fact the dynamics of quantum chromodynamics which is causing this huge amplification of masses from the current quark masses given by the Higgs mechanism to the mass of the proton and neutron, which explains the majority of the mass of the visible matter. So that makes QCD an interesting and a hard phenomenon. If we are studying this continuous Schwinger-Dyson equations methods that I will be focusing on, then in this case, you can try to study the origins of confinement and the generation of mass through the green functions, which quarks and gluons are involved in, like the propagators, the 3-point vertices, the 4-point interaction and scattering vertices, etc. This is a graph in which we have taken one of the elements which form the quark propagator and generally is called a quark mass function, and this is a picture that we get in studying the Schwinger-Dyson equations of quantum chromodynamics in one of the covariant gauges. This is the Landau gauge. And there the picture emerges that this mass function, in fact, of the quark tells us in the Fourier transform space of the coordinate space that at lower momenta these quarks become heavier, and at large momenta they acquire their current masses, which are there due to the Lagrangian of QCD. So when you go to this large P, which corresponds to quarks being very close to each other, then these masses are small, but they have effectively large masses when they try to traverse distances of the size of a proton and a neutron. These emergent phenomena of QCD, as we understand today, are non-existent in perturbation theory, and therefore we tend to associate these phenomena with the infrared enhancement of the interaction coupling of QCD, which becomes enhanced in the infrared region, and it becomes higher than 1, and that is generally enough to produce these large effective masses for the hadrons. As you can see that generally in renormalized quantum field theories, there are quantities of interest that we either talk about as intermediate quantities towards our final calculations of the observables, or the final observables themselves come out to be scale dependent. So you can see on the left side, this mass function of the quark depends upon a momentum scale. This running coupling depends upon a momentum scale. And then somehow the pattern in which these masses of the quark are the function of distance or momentum, in a way, also reflect on the q-square evolution of these pion and kaon and other form factors, where q squared is the momentum of the probing photon, which tries to see the internal structure of these hadrons. So you can see that these quantities are infrared enhanced, and when you go towards large momentum, you tend to reproduce the results of perturbative or asymptotic QCD if you go to very, very high momentum. Okay. So that's more or less the idea of in the type of formalism that I and some other groups work, including the ones who are present here, and you will hear more about it in the talk just after the coffee break. So coming back to the same process, that without understanding the spectrum and transition of hadrons, we expect that neither confinement or QCD or dynamical chiral symmetry breaking, or in general the generation of hadron masses, can be understood. And if that cannot be, then we will not be able to say much about QCD, just like QED would be only understood by understanding the hydrogen atom. So now I've talked about this chiral symmetry breaking, for example, and then one can try to see, okay, how do we see the effects of this in, say, the form factors, or even at a simpler level, how is it, can it be reflected, or some aspects of it in the particle spectrum, or the bound-state particle spectrum that we see? Now, in some way, one can try to get hints of these. You can, if you imagine, for example, on the left-hand side, I have shown these some simple mesons, pseudoscalar meson pion. This is a scalar sigma, vector rho, and A1, which is an axial vector. If, for the sake of simplicity, you consider that they are only made of quark and anti-quarks effectively, then you can write a Lagrangian with this quark anti-quark structure, and depending upon their parity properties and depending upon their isospin properties, you can each of them can be represented differently. And then you can do what are called the chiral transformation or the axial vector transformation. And then you can see that if you do these chiral transformations on these quark and anti-quark fields, then this pion can be rotated into sigma backwards, and rho can be rotated into A1, etc. And if chiral symmetry were a good symmetry, you can probably try to expect that these should have the same masses. But there is a mass difference of about 500 MeVs between these chirally rotated states. When we look at the nucleon structure, then the proton and its first excited, its first parity opposite state, which is n star 1535, also have somehow the same order of magnitude difference in masses. And the same is observed in delta 1232, which is 3½ state, and it's what we believe to be its parity partner, which is about 500 MeV, and that is more or less the mass scale which we see a quark generates when it traverses through the large distances of the size of a proton and a neutron. So one may scale, oh wow, I think probably this chiral symmetry breaking has some sort of effect in the masses that we observe. And so how do we go about studying these mass differences, these form factors, and how they are related to, in general, what we try to understand about the standard model? And as I was telling you that what I study and our group are the Schwinger-Dyson equations. So I'll not go into the details of what these equations are, but I can roughly tell you that these, of course, equations are between the green functions of an underlying theory. In case of QCD, these are the propagators, quark propagator, the gluon propagator, the interaction versus, but all at the non-perturbative level, Of course, you can also study that in perturbation theory, where they become the S matrix expansion of each group, each of these propagator. So these were non-perturbatively studied by what are called the gauge technique by one of the founders of the Standard Model himself, Abdus Salam, in one of his first papers appeared in 1960s. And they studied it in hypothetical quantum electrodynamics, where it would have a non-perturbative solution. Then this was also studied later on by Fomin and Miransky, and Miransky scope kept on to study this QED also in the presence of external magnetic fields, and then also QCD and the bound states of pseudo-scalar mesons in terms of only masses and their mass connections. Later on in 1990s, then the works of Peter Tandy, Peter Maris, Craig Roberts, and the group that they established afterwards tried to study the properties of hadrons at different momentum scales, which not only covers the non-perturbative sides, but also the perturbative sides. So this is the graph that I was showing you, which is in fact the solution of the first string Dyson equations, which is the quark propagator. Once you try to identify your gluon propagator and the quark gluon propagator in the best manner, phenomenologically motivated, and the results that we knew from the non-perturbative studies of these green functions. And then we result into the discussion of the quark mass function that we mentioned before. As I started my talk, I started talking about the bound states. And the simplest bound state, as I mentioned to you before, is a pion, which is a two-particle bound state between up quarks and down quarks. One of them is a particle and one of them is an antiparticle. And we can study this through what is called this bound state equation, the Bethe-Salpeter equation, which is relativistic bound state equations. And that involves, of course, this is a pion in this red blob, and the quark and an antiquark, which are inside, talk to each other at a perturbative and a non-perturbative level all the time through the creation of virtual particles. And the detailed description of this amplitude of a pion can be written in terms of 4 unknown functions, just as the quark propagator is expressed in terms of 2 unknown functions. And it also has this momentum dependence, which will eventually translate into the momentum dependence of the form factors or the charge distributions inside these particles. And of course, the last element that is there is the quark photon vertex. Interestingly, as I tell many times the students that I work with, that we are lucky that despite the fact that the hadron structure is almost entirely given by the interactions of quantum chromodynamics, but we can explore through experiment this structure using electromagnetic probes, because these quarks also happen to have electromagnetic charge, which we are quite lucky. So therefore, for example, the form factor of a pion can be studied in the scattering experiments of electron with a proton converting into a neutron, giving off a pion, and this photon talking to the quarks inside this pion. And you can also have the transition form factors of pions, say, going to 2 photons through electron-positron experiments. And this vertex, of course, has long been studied in its non-perturbative structure and implications in different articles. And I want to mention this third article, which was written a few years ago, especially because we have collaborators from Colombia who participated in it. Eduardo Rojas is one of the authors of this, and also, of course, Bruno Albanich, who is giving the next talk and has been, we have been collaborating together for a long time. So once we have tried to understand the quark propagator and the internal structure of the pion in terms of its Bethe-Salpeter amplitude, how the photon interacts with quarks at the perturbative and non-perturbative levels, then we can go on to calculate the form factor using this triangular diagram. In fact, if we retain ourselves to not very large values of this photon momentum squared, which is transferred to these pion, then we can do these calculations quite precisely. Okay, quite precisely in the sense that we can do all the numerical calculations without having the hindrance or hitting the complex poles if we remain ourselves of the propagator and the beta salpeter amplitude if we stay within about a small range of q squared till about 4 GeV squared. And this, of course, calculation has been done for a long time by different groups, but recently it was redone by one of our postdoc, Angel Miramontes, who's currently in Spain at Valencia. So he did, in fact, he had the chance of working with different groups of Schwinger-Dyson equations across the board in different parts of the world. So what he decided was to use the formalism which were presented by different groups and try to see the consistency between all different approaches, all different numerical techniques, all either doing all numerically or then representing them by some kind of parametric structure, and then doing the calculation and also trying to include the effect of the meson clouds and see the consistency of the results obtained with them. And you can see that the form factor is more or less given quite precisely up to this 4 GeV squared by the calculation that was done by him. One can also go about to do these calculations for the kaon form factor. Experimentally, it is not very well known, at least by now, but we hope that within 1 year we'll get much better results for the kaon form factor experimentally. But one can do the calculations using the same methods quite precisely. One can also use the same elements to study, of course, the pion transition form factor to 2 photons given by this diagrams, in which 2 photons then eventually go into pi 0, or the process the other way, in which the pi 0 can decay into these 2 photons through the current anomaly. Okay, so all this can be computed. This result was also computed by one of our PhD students long time ago using the same elements, and that calculation can be done to much larger values of q squared, this effect. Okay, but use the same kind of elements, and those are in a way related to what are called the distribution amplitude of the pion, about which I will actually not talk about it, and I'll leave probably Bruno in his next talk to be talking about this. So I'll focus myself only on the pion form factors. Now, why are these form factors interesting? Of course, there are 2 things. One, I told you that it tells us about the internal structure of the pion or the kaon. It tells how QCD creates this charge distribution, or where the quarks can be found inside these hadrons. And not only that, but eventually these form factors also help us study the standard model in its full glory. You know that we can do many precision calculations of the standard model to try to understand how far we can continue to go with the standard model that we already know, or if there is any physics beyond that. So these low q squared computation of electromagnetic and the transition form factors of pions and kaons, in fact, help us understand one of these, almost all of these precision observables, and very importantly, this anomalous magnetic moment of the muon. Well, it's of course this typing error here. I can already, if you try to fix it, some muon anomalous magnetic moments is not a mon anomalous magnetic moment. A muon, we know there's spin half particles, whose magnetic moment is defined as such. In fact, the Dirac equation told us this gyromagnetic factor that appears here, G, for the spin half particles is exactly 2. But then, of course, the work of Schwinger and others through the renormalization QED tells us that we will get corrections to this quantity and other quantities like the Lamb shift. And the leading computation to correction to this was calculated by Schwinger himself in 1949 through the one loop contribution to the electron photon vertex. Okay. You can write the amplitude of a muon scattering off an external electromagnetic field by this current. There is an initial muon, the final muon, it is connected through an electromagnetic current. And that electromagnetic current in general, when you have these on-shell initial and final muons, can be written in terms of two tensor structures, and one of them corresponds to what we know as the Dirac form factor, and the other is the Pauli form factor. And in fact, it's the Pauli form factor evaluated at q square equal to 0, which gives us the magnetic moment, and that has to be computed at different orders of magnitude. Now, of course, there are different contributions coming to this anomalous magnetic moment. There are weak interaction contributions, QED contributions, but one of the contributions which is important is the hadron light by light scattering, which appears at order alpha cube as compared to the vacuum polarization contributions, which appear at order alpha square. And I was telling you why these form factors that we compute are important, because these appear as intermediate processes in the study of this anomalous muon magnetic moment. You can see, for example, in this particular diagram that I'm trying to show by my cursor, if you can see it or not, is a pion p pi 0 going into 2 photon or any other pseudoscalar meson. And then we have these circle diagrams that in fact are called the box diagrams, in which you can have the charged pion loop, and you can study that this in fact couples to this photon which is interacting with the muon, and therefore this corresponds to a photon probing the charge distribution inside a pion. So both the electromagnetic and transition form factors appear as intermediate scattering processes in the computation of this hadronic light by light scattering contribution to the muon anomalous magnetic moment. And of course, people have calculated it. It has been reported in this working group that keeps updating every few years in this white paper that is written by the working group of muon anomalous magnetic moment in 2020. It reported the values by this, not only by phenomenology, dispersion theory, lattice QCD, and also by Schwinger-Dyson equations. I showed some particles here in blob. You can also have the eta C and eta B, which contribute, of course, less, but we have recently computed these. And you can also have these radial excitations coming instead of the pion and kaon ground states. Okay? All this can contribute. I will not go into the details of these computations. I can just mention that in the last several years, our group has tried to compute the contributions which come from these particles in different articles, and we have reported them over the period of last 5 or 6 years. For calculating the contribution of the transition form factor of pi 0 going to 2 photons, you have to, in fact, generalize this process in which pi 0 goes to 1 on-shell and 1 off-shell photon to both these particles being off-shell, which is a requirement of internal propagators appearing here. And one can then, after generalizing it, do the computation, and once you do the computations, then you can see that the result and its numerical accuracy, due to the work that was done by Angel Miramontes to quite a precise level, our accuracy level is not really any different from the results which are given to us by lattice QCD calculations or dispersion methods, etc. And they can come out to be in the same ballpark, and also agree with the results computed by other group of Gernot Eichmann and the other collaborators that they have there in Austria. And similarly, you can also have this charge pion and kaon loop diagrams you can use to compute also the effect of this loop or the box diagrams to this anomalous magnetic moment, and that was also done by Angel Miramontes, Kepani Raya, and Pablo Roch and us in a recent computations. And more recently, In fact, only about a month ago, we have tried to compute for the first time how much this contribution will be reduced if in this loop, instead of the ground state pions and kaons, we have the first radial excitation of these particles. And this we have put on the web page only about less than a month ago. Okay, so this was the implication that I was talking about, these form factors for low q-squared values, how it tells us about the standard model of particle physics, and how we can try to have the effect of the hadrons computed in the precise measurement of the observables, which in fact help us understanding the depth to which the standard model can be tested in experiments as well as in theory. Okay? Now, on the other hand, these form factors in themselves are important because that tells us about how QCD is at work, not only for low q squared, but for large q squared. Now, at this point, I must mention that because QCD has its perturbative and non-perturbative facets on both sides, it's not always easy. Because experiment can tell us what happened at one end of the spectrum, and asymptotic QCD tells us what happens at large values of q squared. And one of the aims of the hadron physics labs and the computation is to be able to study, for example, this q squared dependence of the pion and kaon elastic form factors from low q squared to large values of q squared. Low q squared is where so far the experiment tells us. And then this 12 GeV upgrade of the Jefferson lab, which is whose data is now being analyzed, would be able to tell us about the form factor of the pion to larger values, say about 6 GeV squared. It still is apparently far from the asymptotic limit of QCD, which we expect to set in at a higher values of q squared. What we may start seeing these scaling violations at a much earlier region. So the pion form factor from this 12 GeV upgrade of the Jefferson lab, we expect that it will be telling us it will be computing these form factors of pion to 6 to 8 GeV squared, and it will also be able to compute the kaon form factor till about 5 GeV squared in these experiments. Okay. So that is more or less the reach here, where it is showing where we will be able to know the pion form factor in this light blue diamonds when the results are available. Then there is also has been this proposal of this upgrade of this Jefferson lab at the 22 GeV energies rather than only 12 GeV. And it, in fact, there was the first workshop held in 2023 in January, when I was doing a sabbatical year there. And this potential upgrade of 22 GeV would be able to tell us, would be able to compute this pion form factor up to about 15 GeV squared. So these light blue diamonds go up to about 9 GeV squared, 8.5 GeV squared, and then the further analysis with this 22 GeV able to measure this to about 15 GeV squared, which is quite nice. But then, of course, we will also enter in the next decades into the electron-ion collider era, and of course, for them, the key questions of science, that is the emergent pion mass and how is the overlap between the Higgs mechanism mass generation and the QCD mechanism of mass generation. These key questions also require the measurement of pion form factor, which will be able to be done in EIC till about 40 GeV squared from 10 to 40 and 10 to 20 for the kaon. And therefore, we will have a broader picture thanks to what is being done at JLab, what will potentially be done there, and what will eventually be done at the electron-ion collider, extending the domain of this 12 GeV upgrade, what has been known before, to the 22 GeV upgrade, and eventually this black squares and the associated error bars will be the results we expect EIC to tell us in next decades. So that is more or less that I was wanting to talk about the form factors of pion and kaon. And as I mentioned, these Schwinger-Dyson equations and the results that I showed us so far imputed were using these sophisticated truncations of Schwinger-Dyson equations, and which allow us to compute this QCD green functions at least to some, say, not very large values of Q square. But then there are other ways of truncating it. We have some very brute force truncations, which only, in fact, allow us to compute these measurements at very low Q square, and basically only the static solutions of hadron physics, which is the contact interaction. But we can also rely on what are called the algebraic models, in which we rely on our results from the refined Schwinger-Dyson equations computations. Using those, we build models for QCD, and then those models, we expect and hope that we'll be able to retain the Q square evolution of these form factors, not only for low Q square, but large Q square, allowing us to go to large Q square, which will not only probe the existing experimental scales explored, but the upgrades of Jefferson Lab and also the EIC measurements in future. Now that I'm reaching almost the end of these, I will not be able to talk about the algebraic model. I'll just try to briefly tell us that based upon our computations of the Schwinger-Dyson equations, what we can do is to assume a particular form for the quark propagator, assume a particular form for the Bethe-Salpeter amplitude written in terms of an unknown spectral density. And then, of course, these inputs of the quark propagator and the Bethe-Salpeter amplitude and this spectral density, then we feed them by certain forms based upon our understanding of these green functions, and associated with some, of course, unknown parameters, fix these parameters with some observables, and then for the rest of the observables, make predictions the way usually models do. So these is a usual way of working with algebraic models for hadron physics. Some of our group members have worked with this algebraic model for the last 2 or 3 years. We have tried to make quite a general algebraic model in which this spectral density, which was originally depending upon this constant lambda, which was generalized to a more complicated structure, which allows not only us to study isospin symmetric limit, which are restricted to like protons and neutrons or deltas, which are composed of U and D, but also to hadrons, which have different flavors, and this extension to other parameters like a slight deviation from the large Q square behavior of the amplitude will allow us to include this logarithmic corrections to this small parameter nu, and look at the scaling violations possibly. So this algebraic model we used then to compute the light front wave function, which I will not go into the detail. I will leave it Bruno to be talking about it more in his talk that I'm sure he will be taking up. And once you have this light front wave function of this pion and kaon, then you can use this what is called the overlap representation of GPD in terms of these light front wave functions, and you can calculate and give the 3-dimensional picture of this pion and kaon in terms of this Q square dependence, in terms of this momentum fraction dependence. And in fact, these plots have been drawn in with the off forwardness equal to 0. So once you have this, of course, you can compute different limits. You can calculate the Barton distribution functions at the hadronic scale. Then you can evolve it to the experimental scale and try to see if your results agree with what we currently know about this distributed the pion distribution function, the pattern distribution function of the pion, for example, and how well we know at the scale where the experiment can see it, and both for the pion and for the kaon. So I have skipped almost all these details here, but what I want to see is that the limiting cases, of course, of this one, the lowest moment of the generalized pattern distribution functions, in fact, also give you the form factor. So we can compute this GPDs through this algebraic model and then take the lowest moment to calculate the pion and kaon form factor. You can also use the triangle diagram to these form factors, but with the advantage that now you can go to largest values of Q squared. Okay. So first we tried to check the validity of these algebraic models for low values of Q squared and try to see if we could reproduce the results that were given to us by Angel Miramontes calculations of more precise string and Dyson equations result till 4 GV squared. And we find that the agreement was pretty good. And the same we saw for the kaon, although when we go to large Q squared, then the parameter dependence of these algebraic models provide a bigger spread when you go to large Q squared and you don't remain that precise, and that was of course to be understood. But of course the advantage is that then you can go to as high Q squared as you basically want. And if you do this higher Q square calculations, the right side of the diagram tells us that we can extend this algebraic model, which will cover not only the current range of experiment, but the 12 GV upgrade, the possible 22 GV upgrade of Jefferson Lab, and also to the EIC limits going up to all the way to 36, 37 GV squared. So this light blue band comes from these algebraic model calculations that we have performed. This is red line is the early Dyson equation results produced by Craig Roberts and his group, and this is what we report. We can also do the same thing for kaon. For kaon, we have only reported here in the article up till about 8 GV squared. This projected results that we will be expecting soon coming from the 12 GV upgrade on the left side given by this red diamonds. These are the same diamonds on the right hand side, but now they have been replaced by this blue diamonds, and we will be covering this region where we will soon be, I think within a short time, the results for the kaon form factor. We also have these lattice results which have recently come this year in the mid this year, June or July, from the BNL group on lattice studies of kaon and pion form factors. So basically, this is where I stop and just provide you a small summary in which I can tell you that there has been a lot of time spent on studying these form factors of pion and kaon for last several years. I focused more on the paper of 2022, which was of course performed by one of our postdocs. Then you also have, of course, go not only to low Q square, but you can go to higher Q square. You can use the algebraic models to go there. You can also do, in fact, a time-like computation for these pion and kaon form factors to study the appearance of resonances that I did not cover in this talk. Then I focused in the end the carefully constructed algebraic models. I only focused on the first 2 articles of this, but you can, of course, you can go on to complicate these algebraic models and try to implement confinement. This is one of the articles that we put on the web a couple of months ago with our Chinese and Pakistani colleagues, and you can make your algebraic form factors better and better. So all this can be done, and also as a last step can be extended to the study of baryons. You know that Jefferson Lab is one of the places you can study the baryon form factors and the transition form factors of these baryons going to their excited states and higher resonances. And we can carry on these computations to try to make predictions for their current and future experiments. So that's where I would start. I will thank you, but before I take on a couple of questions, I would like to tell you that the next week there is going to be a workshop, a second workshop on the science of the luminosity frontier of the Jefferson Lab. It will take place in Frascati, Italy, and they'll be talking about the advantages of this 22 GeV upgrade that we'll be having at the Jefferson Lab. And just another promotional slide that for the first time, we will hold a conference. It's actually a 10th annual workshop on particles and fields, but for the first time, it will be mostly focused on QCD, hadron physics, and the internal structure of proton, neutron, pseudoscalar mesons, and other baryons and mesons. And we'll be happy if some of you can come and attend it. So that's where I will basically stop, and I will probably leave it here. And thank you very much for your attention.
I have a question regarding the pion form factor. So as you certainly know, last year CMD3 published their results for E+, E- annihilation into pi+, pi-, and they were in tension with essentially all other experimental data sets before that. And there is also, for the case of the muon G-2, this issue for the lattice estimates of the vacuum polarization, hadronic vacuum polarization estimate. So I was wondering if maybe you could comment on that. For example, what could Dyson-Schwinger equations tell us about this conundrum regarding the pion form factor?
Okay, thank you for this comment. I was expecting somebody would probably talk about this. As you might have noticed that when I was talking about this hadron light per light contribution to this muon G-2, I focused only on the results that are related to HLBL, and I didn't say anything about the vacuum polarization diagrams. Now let me just come back to this, although I don't know, putting it here, it does not help much. But of course, as you see that the main conundrum that we have had for the case of G-2 comes from the vacuum polarization diagram. And of course, the vacuum polarization diagram would Schwinger-Dyson equation. I think this Austrian group had given some results about a decade ago, but the error in the results is quite large, and that at that point was not competing so much with the accuracy that we require to really talk about this conundrum and see if the computed results is far from the experimental result, or it goes as close to it as the BMW lattice calculations suggest, which tell us that in fact I was there in this 2024 workshop that took place in Cairns in Australia in August, and they told us that this recent calculation of 2024 tell us that this vacuum polarization contribution that comes from these hadrons, in fact, reduces the error to only about 1.9 sigma of this conundrum between theory and experiment for the G-2. Now, you asked me about the Schwinger-Dyson equations. More recently, in fact, Angel Miramontes has been developing the required machinery to do this computation for the vacuum polarization within the Schwinger-Dyson equation scheme, because now we're able to study more precisely the photon quark vertex that was causing, in fact, most of the error in this computation earlier. I can't tell you, but we might be able to produce some results. Can't say to what precision level using Schwinger-Dyson equations. But I also want to tell you that the contribution which comes from the pion itself, in fact, already has about 75% of all the contribution. This comes from the vacuum polarization diagram. So in fact, pion does play a very important role. And I just hope that Shinga-Dyson equation would soon be able to say something more precise and more competitive in near future on this observable.
I am Eduardo.
Hi, Eduardo. How are you? I know you are
Fine,
Eduardo.
fine. A question is, did you mention the generalized Parton distribution functions? Then I also hear about polarized Parton distribution functions. Which is the difference between a polarized Parton distribution functions that I assume are designed to solve the proton spin problem and the generalized Parton distribution functions? This is the first question. So which is the difference? I am not an expert on this subject, so okay, sorry for the ignorance. Second, it is possible to measure these Parton distribution functions, or maybe already they have already measured. The third question is, it is possible to calculate these quantities with by using Schwinger-Dyson equations or the FADEP, in this case, in the case of baryons, the FADEP-Popov equation, the FADEP equation. Yeah, this is my question. Okay, thank you, Adnan, for very nice talk again. Okay, it's good to see you.
Okay, thank you very much. Yeah, Eduardo, it's very nice to see you as well, but I'm not going to answer any of these questions unless you promise me that you will start participating in computing those. Because I think that you have a lot of machinery developed in the study of Schwinger-Dyson equations and Bethe-Salpeter equations along with Bruno, and you've also worked with Craig, and I hope that we will try to drag you back into doing these computations. As you know that, well, let me just go slightly off the road. And then, you know, one of the things that I didn't mention was studying, say, for example, the spin-1 particles that I think that Eduardo Rojas himself has studied, rho particle. And then you have these axial vector particles. So one of the things that is interest for the G-2 things is for people to be able to study this axial vector mesons going into 2 photons and then see what kind of, how much effect it, that is something a bit more urgent that we people have been asking us to study through Schwinger-Dyson equation, the axial vector going into 2 photons, and how does it contribute towards G-2. But talking about this vector particles, then and the polarized targets, you know that in HERA people have studied and people continue to study this deuteron wave function, because you can in a way make these deuteron polarized targets. Okay, and then you can study this structure functions, which are or eventually also the form factors one can study, which are also polarization dependent, not only spin dependent but polarization dependent. So there, in fact, instead of just being 2, I think there are about at least 6 structure functions which are spin dependent and polarization dependent, etc. And that also, of course, depends upon in the experiment how can you you can have polarized targets, and once you have polarized targets, then you can try to address these questions. And of course, whether you can use Schwinger-Dyson equations techniques or not, then I expect that eventually we will be, but that will, of course, demand a lot more manpower to be able to do so. Of course, I don't know if I answered you in the detail that you wanted to know, but I hope that you will yourself be able to participate and you find this talk and our work sufficiently exciting to join us in doing these computations and eventually solve the puzzles that we don't solve. Some of the puzzles I've talked about and some of the things that you have mentioned, like the proton spin, and let's see what we can learn from this.